Hello, and welcome to CE721. And thanks for taking this course. It should be a lot of fun. It's run for a number of years. It's 100% coursework, which tends to make it quite popular with students because it's no exam. But don't be fooled into thinking that this is an easy option because the number of hours that you have to spend on this is quite considerable. We're in the lab for 3 hours. And there's an expectation you'll put 3 hours in on top of that as well. So a lot of time spent on it, but I think most people that take this find it to be really good fun. One of the things about this is if you look down the syllabus, you'll see that it takes you through the design steps of producing an electronic project. Sorry, I'll start that again, an electronic product. And that electronic product, we need to design the PCB for, we need to test it and all the rest of the stuff that goes with it. But at the end, there's an expectation that what you make would be deliverable and you could actually sell it. Now, that makes you highly employable for small to medium enterprises or even really large companies because you understand the production cycle and can actually make things basically. So the employability after this module is very high, and I quite often get people jobs in and around the Colchester and Essex area associated with printed circuit board companies and electronic companies. So yeah, it can have some good outputs. So objectives, what are the objectives? At the end of this, I want you to be able to design a multi-layer printed circuit board, preferably with surface mount components, although through hole is acceptable and you will pass if you do through hole. You'll need to show through simulation that your circuit works before you even design it. And before you, or while in the process of designing it, you'll also test it with discrete components. So you'll wire it up and test it with a real oscilloscope, real signal generator, and all the rest of it. And then you'll go on to do that in simulation as well. And you'll make a comparison between the two and hopefully draw some conclusions. So the objectives at the end of this to be an electronic design engineer. Does that mean that you have to understand the circuits perfectly? No, it doesn't, because the majority of circuit designers may not understand all the circuit or even some of the circuit, but it doesn't stop them putting something together from reference. So as long as you've got a circuit diagram, you can piece it together, you can run those simulations, and you can make the printed circuit board. I invite you to have a look at the learning objectives, but it's pretty much what I've just discussed with you. It's the main objective is to be able to design and deliver a working commercial product at the end of this. And we generally send our PCBs away to PCB Way, strangely enough. And those PCBs come back within a few days, and then you can populate them with the components, soldering them on yourself. And we'll show you how to do surface mount soldering under microscopes or using the reflow oven if they're too small to be able to do by hand. And we just show you the whole process. We've got a pick and place machine because quite often the components are so fiddly you can't do them by hand. And in that case, we'd lay them out on a mask and the pick and place machine will put them in the right position. We put some solder paste over it and reflow it, and thereby we would solder it to the board. Okay, the tools we're going to use, well, we're going to use multisim. You can use another simulator, but we can't necessarily guarantee that we can advise you on that because you may know an existing simulator better than us. So I would encourage you to use multisim. It's available on all the machines in the lab. You can also get it on Horizon, more of that when you come to the laboratory itself, but you can use that dedicated software outside of the laboratory time on your own machine. So that's quite handy. And it allows you to do some work outside the lab. Now, the labs themselves are 3 hours. They are on, I'm just looking up myself, Tuesday, 11 o'clock until 2 o'clock. And so that's 3 hours. And I have an expectation, as does the school, that you'll spend another 3 hours of your own time outside of that. So really, this is 6 hours work a week. So it's 60 hours in total. And I think you get some kind of idea that you can achieve something reasonably substantial in 60 hours. So that's where we are on that. As far as other tools that we use, well, we've got Roden and Schwartz signal generators, oscilloscopes. We've got pick and place machines that you're welcome to use, microscopes, dedicated high-end soldering machines, pretty much any of components you'll ever need. And if we haven't got those components in the drawers, we can soon order those for you with a few days lag. So we've got our hands on pretty much everything that you'll need. The level of the circuits you're going to design aren't unbelievably complicated just because of the time that we've got here. But typically, I would expect, the second design you're going to use is going to have about 30 components on it. So, but we're not talking about something of the complexity of a computer, because you can imagine a motherboard, how many components that's got on it, and so on. We just don't have the time to do that. Okay, so as with most students, how do I get the grades? Well, this is 100% coursework, as I said earlier. Doesn't necessarily mean that it's an easy option, though. There's 2 assignments, 50% for each one. It's not quite as clear cut as that, because I get to know you so well in the lab because of the amount of time we're spending in the lab, that you're kind of orally assessed as you go along. So I'll come round, I'll spend some individual quality time with you and talk to you about your report, and we'll be talking about the circuit design and the report in parallel. So when I actually come to mark your report, I also know what contribution you've had in the lab. I don't necessarily write it down and say you've got 10%, you've got 20% for the oral. It's not like that at all. But I am fully aware, even with large student numbers, the contributions that people are making and what their circuits are and any problems they've had with it and so on. So it's a bit like a continuous assessment and continuous feedback. So if you want help, put your hand up, and generally, if one person has a problem with one thing, then you just tell everyone what that problem is and we solve it collectively. Do you need to have sim multi-sim before? No, you don't, because the first 2 weeks I take you through on the projector. So I project what I'm doing on my screen and you copy it. Absolutely, literally, from start to finish. And we design a potential divider first, then we design a high pass, low pass and band pass filter. And then by the end of the second week, I say, right, here's a circuit diagram. Go away and draw it yourself. And believe it or not, within week 3, you'll have a circuit that not only looks quite impressive and is exported to a PCB, but it actually works as well. So, and then after that, once you can walk, you run and you start work on your first assignment. So, like I say, 50% for each one. The reports are typically less than 10 pages, please, because that includes diagrams, graphs, tables. Why? Well, because this is practical based. This isn't an exercise in writing a formal report. This is, have you got the hand skills necessary to produce these products under an industrial setting? Okay, so grading method 50%, that's fine. So what are the assignments? We change them each year, but this year what we're going to have for assignment 1, and the due date, I did write this down, just let me check. So the due date for the first one is the 26th of February. Bear in mind our first session is on the 13th of January. This is all on the webpage, by the way, you haven't got to remember this. So the 26th of February is the date for your first assignment submission on Phaser, and you need to check the times for yourself and all the rest of that kind of stuff. The first assignment is a photo popper, which is a lot of fun. What does that represent? Well, if I plug a small solar panel, and by small I mean small, here's an example of one. I'll just hold it up here if it comes out on the camera okay. You can see a pretty small solar panel Not enough to drive a small electric motor, but that's exactly what we do want to do with it. So how do we do that? There's not enough power coming off that little panel to drive a motor, so how can we drive a motor? Well, what we do is we store it on a capacitor, and then we dump the energy from the capacitor into a small motor. And in doing so, we create a small robot which is capable of moving itself with that motor, but there's not actually enough energy coming in theory, for it to be able to do it. So it's kind of store and dump, store and dump, store and dump. And there's some wonderful circuits on that. So just look up photo popper and you'll see that people have been fiddling about with these circuits for some considerable time. They go from very, very simple to very, very complicated. And I've got a research area that's looking at powering microcontrollers by similar means for, excuse me, for inventory control. Assignment 2. So that means you will have submitted assignment 1 on the 20th of February. You then start working on assignment 2. Assignment 2 is due on the 20th of March, again on phaser. Same methodology. I'm coming round, I'm watching over your shoulder, checking what you're doing, helping you wherever I can. And I know what you're working on, and I know that in some detail. Assignment 2 is a circuit of your choice. So think of something that you would like, something that's actually useful to you. And there's lots of different things that you can make: an amplifier, a filter, a mains inverter, although we don't use mains, but a bar graph generator for that shows you the energy levels in music, a small radio receiver, a small radio transmitter. The list just goes, a metal detector actually last year. The list just goes on and on and on. How that works is you do a little bit of research, a couple of hours will do fine, find a circuit you like, then you have a discussion with myself and the teaching assistant, and we say, yep, go ahead and make that, or possibly, no, don't do that, it's too complicated. Okay, your first assignment, you don't have to produce the PCB, but I would like to see the PCB in the simulator so it shows that you could make a PCB. In the second assignment, if you want a good grade, I'd like to see that go off to PCB Way, and you send off the Gerber files and they send you back a printed circuit board. We'll pay for that if you want that made, but you'll get back this printed circuit board exactly as you designed it. So if you made a mistake in the design, the components won't fit on there. So it pays you to be very sure that what you're doing is right all the way through. And then you can populate that with the components, and then finally you can test that on the bench and verify that it works. And well, I suppose you could open up your own company on eBay and start selling them if you wanted to. So yeah, a bit of a challenge there. Ways in which you can test a circuit board. Well, you can do what's called rat's nesting, which just take the components and either solder them or twist them together so that they're floating around in 3D space. Often used for RF circuits because there's no parasitics attached to it, but not the best way to do it in the world. Veriboard is another way. You can just push the components into little holes and they make the connections automatically for you. Downside is you get dirt in those holes and corrosion on the copper track, so they can be unreliable. Veriboard is kind of a halfway house between breadboard and the printed circuit board, because you actually solder the components in there and it's permanent. I mean, you come back to it in 50, 100 years time, it probably still work. So Veriboard's quite a good way of doing things. And there's other more hybrid methods by which you can prototype a circuit. But so you come up with a design, you run it in your simulator. Your simulator says it works because you get a graph coming out that makes sense and you can measure voltage levels and so on around the circuit. But there's no real replacement for actually building it. And you don't want to go to the expense, not that it's that much, but making a printed circuit board only to get it back and find that you've made a mistake on it. So it pays you to verify that things are working first. Okay. And this 10 weeks will go like a rocket. I mean, it's a complete load of fun for everyone. And we often get students who are not doing 721 from the first and second year of our undergraduate, who come in because we're the only module that takes you from the very, very simple to the very complicated in that period of time in electronic circuit design. Okay, I'm not sure I need to say much more at this stage. It becomes very, very obvious. What's the theory behind this? Do you need to study theory? You don't, but there is some nice theory on the web to explain things like the operation of capacitors, resonators, all this kind of stuff, if you want to know. But this isn't an exercise in understanding complex circuit theory. This is an exercise in producing a deliverable, and that deliverable is a product that at the end of this, we want to be able to say that we could sell it. And that's what your boss in a small company would want. Okay, I'll leave it there. I look forward to seeing you in the lab, and I must confess, for all my sins, this is one of the modules I enjoy the most in my career. So hopefully my enthusiasm will come across and make you enthusiastic towards it. I look forward to working with you. See you soon. Bye bye.